Let's start with monomorphism and epimorphism. So monomorphism is also called monic in Bell's book. So definition, monomorphism is in arbitrary category C, you have a morphism from object B to object C. F is called monomorphism if for any other object A and any other two different morphisms. Fe1, which means F composed with E1, is different from F composed with E2. In other words, we said we can cancel from left. F, or we can cancel F from left. Because if F alpha equals F beta, then F monomorphism implies alpha equals beta. Okay. And epimorphism is similarly, F is called epimorphism if you have some object D, you have E1, E2, then E1 compose F, it's different from E2 compose F if E1 doesn't equal E2. In other words, you can cancel F from the right. So if you have F alpha compose F equals beta compose F, then this will imply that alpha equals beta. Okay, so important thing is what is the relation between this epimorphism and morphism from our intuition of injective and surjective map. Good thing is for injective and monomorphism, they are totally the same for concrete categories, which means the underlying, which means the objects have an underlying set. This, in most cases, we got groups ring sets. In that case, monomorphism is the same as injective map, while for epimorphism it's not the case. The argument we could have is surjectives in concrete category implies epimorphism, but epimorphism doesn't imply surjective. So let's say this exercise. 8.1.1. The first counterexample is in the category of ring. This ring homomorphism from Z to Q. Obviously not surjective, but is an epimorphism. Second counterexample in the category of tautological spaces. So embedding Q into real numbers is epimorphism. So here the topology is just matrix topology, for example. Okay. So solution would be, let's call this F, call this G. So we're just going to check its epimorphism is to check. Either we could cancel F from right hand side. In other words, if you got use FGH, you have H1 compose F equals H2 compose F. So this will be a map from J to Q into whatever ring. Here you got H1, H2, and can you show that H1 equals H2? Answer is yes. So this is the idea. Answer is yes, because you just have to check H1 over M over N, M and integers. You just have to realize this is. So we are assuming this ring homomorphism requires identity map to identity. Okay, even if you don't require this argument should still work. So in that case, this is just realize this is H1 of M times H1 of N inverse. And so it equals H2 of N times H2 of N inverse. And this is H2 times N, because we have, for example, H1 times N equals H1 equals 1. This is telling that the invertible elements in R and they inverse to each other. And so this is telling that we're only using the fact the restriction to Z or the composition with F equal implies they are equal. For similarly, topological space, let's call it T. You just have to notice that H1 for any element's real number X is just its action on limit of some xi rational numbers, and because H the homomorphism in topological space, category of topological space is a homocontinuous homomorphism, and so the limit, sorry, should not write arrow, just limit commutes with this function, continuous function, and over Q H1 equals H2, and so this implies H1 equals H2 for any object in real numbers. And so this also implies that what I'm saying is that similar here, H1 compose J equals H2, compose J imply that H1 equals H2.